All right. Okay. We are up to example 8 in the notes and tool number 7. I think this may be the last tool. I'm not sure. This is definitely the tool of last resort. Sometimes you start working on the side that you think looks most complicated, which is what we've usually done. And we work and we work and we work, and we just can't figure out how to get it to be the other side. Absolutely cannot figure it out. Well, it is legal to work on one side as much as you can, simplify it as much as you can. And then if you absolutely get stuck, then completely independent of that, you can start working on the other side and work on it as much as you can, and just show that the two sides equal the same thing. So I may not on this problem directly be able to show that the left-hand side equals the right-hand side, or the right-hand side equals the left-hand side. But if I can show that they both equal the same thing, then I still will have accomplished verifying the identity. So, any, mini, miny, mo, which side would you probably start with? I would start with the left. And this is example 8 in the book. So I would get a common denominator, multiply the first term by 1 minus sign over 1 minus sign, second by 1 plus sign over 1 plus sign, combine like terms, or add the numerators, keep the same denominators, and then combine like terms. So far, so good? Can you think of anything else I can do to that? I could fall out the denominator. Oh yeah, I could fall out that denominator and give me 1 minus sine squared, and in the place of 1 minus sine squared, I could put what? Cosine squared? Well, it wouldn't get me to the right-hand side, but it gets me to something. Yeah. All right, so 2 over cosine squared, or how else could I write 2 divided by cosine squared? 2 times secant squared. Yeah. Now, you know what? I think I just figured out a way. I copied this from the book, but I think I could make that into the right-hand side, because what is another way to write secant squared?
2 times
1 plus tangent squared. And then if I distributed the 2, I'd have 2 plus 2 tangent squared. So I don't know why they did this one working on both sides independently.
They just wanted the trick.
I guess they just wanted to show us that it's legal. Okay, let's see. Yeah, it looks like whoever wrote this example for the book stopped right there and said, I can't go any further. Fine, I'll work with the right-hand side. So the right-hand side is 2 plus 2 tangent squared theta. You can write that in terms of sine square and cosine square. And then what? Get a common denominator, multiply the 2 by cosine square over cosine square. Add the numerators, keep the same denominator. Factor a 2 out of the numerator, and that leaves you cosine square plus sine square. What can you put in place of cosine square plus sine square? 1. So that also equals 2 cosine squared theta. Now, the way that it's done in the book, they showed that the left-hand side equals 2 over cosine squared, and the right-hand side equals 2 over cosine squared. Therefore, the left-hand side equals the right-hand side. We just saw that there was a way that we could have gotten around that. All right. I wonder then if there was a different way, if we could have done number 14 by starting with the left-hand side and only working on it till we get to the right-hand side. I don't know. Let's try this one for 14. Yes, the numerator of the first one is a perfect square trinomial. So where's my image mate? Oh, I have a lot of stuff open. There we go. That's number 13. 14. Oh, there it is. Okay. 14. All right, the first time I used these notes, that T on the right-hand side was missing. Do you have that T? Okay, I corrected it then. Definitely, I think the left-hand side is the more complicated side. So that's what I'd start with. And y'all did such a good job of the format in which you did your homework. Every problem said show that this equals that. And then you recopied the side that you wanted to start with and worked on it till it became the other side. So y'all did a great job on that. And the first thing that Miss Carey noticed about this one is that numerator is a perfect square trinomial. How would it factor? Cosine t plus 2 squared. And I would never go on any further in this problem without double checking that factoring. If I wrote it down twice, I'm picturing it in my head as cosine t plus 2, cosine t plus 2. Sure enough, that'd give me a cosine squared t. It'd give me a 2 cosine t for the outer terms, a 2 cosine t for the inner terms. That would give me 4 cosine t. And then I'd have a 2 times 2 is 4. So far, so good. And then what? Well, obviously, one of those takes out one of those. This is just cosine t plus 2. Yes.
So the denominators are 1.
Yes.
So couldn't we like substitute something in for the 1 to make it that? Or no?
I mean, there are a lot of things that equal 1.
But like I like cosine squared
yeah.
plus sine squared.
Off the top of my head, nothing is jumping out at
Could
me.
you change the sine squared into 1? Oh, that's what I was thinking.
Yeah, I'm running through all kinds of things, but I don't, off the top of my head, see anything that I could do to suddenly make that become, well, maybe. Oh, I did just think of one thing. How could I change a cosine to a secant? I could, in the place of cosine, I could put 1 over secant. I think that's actually going to work. 1 over secant t plus 2, because what could I do then? Get a common denominator? Look at that. We don't need that tool.
Yeah.
Say that again. I don't think there's one where you could not get from the left-hand side to the right-hand side without having to do both sides independently. The question's going to be is how long are you going to stare at this before you just give up and go, well, let me work on the other side. So it's not that you can't, It's just that if you get absolutely stuck and you don't happen to think cosine is just 1 over secant, then starting with the other side and showing that it also equals cosine t plus 2 is a valid way of doing the identity. All right, I like that we figured that out without having to resort to using that work on one side and then the other tool. So look what's next. I'm so excited. Yes, it is. Oh, stop. I can't. There we go. I have to sneak up on it. Yes. Holy cow. That's verifying identities with trigonometric and logarithmic expressions. And we don't really have a new tool for this. We just have all of our properties for logarithms that we know from college algebra, algebra 2. We know that the log of a product can be written as the sum of 2 logs. And going backwards, the sum of 2 logs could be put back together as log of a product. We know that the log of a quotient can be written as the difference of 2 logs, or going backwards, the difference of 2 logs can be put back together as log of a quotient. And we know the log of something to a power, the power can just be put out front and multiplied by the log. So we have some tools. They're just not tools that are new to us with trigonometry. So which side would you start with? Just take a deep breath. Oh, yes, Miss Madison. And even those bars and something special about 2 straight lines. Value. And the absolute value, here, you don't have to do anything with it other than keep up with it. But the reason is if you use the absolute value of sin x, then you can use more values for x. You could use x's whose sign is positive and x's whose sign is negative, because you're going to take the absolute value before you take the natural log. You can't take the natural log of a negative. But because of those absolute values, you can use any value for x. There's still one thing you can't use on this second term, secant x. What could you not let x be? Not because it'll give you a negative, but because of something else. I'm thinking secant is 1 over cosine. So what can we not allow to happen? We can't allow cosine to be 0. Cosine's your x coordinate, and where your half pi, that is your y-axis. You were right. So I still couldn't let x be any odd multiple of pi over 2, but at least I could let x be values that would cause secant to be negative or positive. I just need to keep up with them. Which side do you want to start with? Any, mini, miny, mo, doesn't matter. I'm not sure which one I typed. Looks like I started with the left. No, I did. Yeah, I started with the left. I wrote natural log of absolute value of tangent x is the same as natural log of sine x over cosine x, because that's the definition of tangent. Sine over cosine. So far, so good. And then I just used the property regarding natural log of a quotient can be written as what? Well, it looks like in order to get a secant out of that, they needed to separate the fraction sine over cosine into sine times 1 over cosine, because you're keep looking back up at what you're going for, and you want a secant out of this expression, you're going to have to write that cosine in the denominator as 1 over cosine. And then, Miss Haley, They're only working on the left-hand side, so don't look at this for a minute. Just take the left-hand side and write that tangent as sine over cosine. Okay, and then write the sine over cosine as sine times 1 over cosine, and then of course, in place of the 1 over cosine, you can put secant, because you want to end up with a secant in your answer. So what's the one tool that gets us from where we are right now to the right-hand side? The log of a product can be written as the sum of two logs. That wasn't hard. It was scary as heck when it popped up on the screen, but it actually wasn't hard because I know my properties of logarithms and it just fell out from there. So can we do some? That's the first one. I am in slideshow mode. I'm not sure why all of that popped up one. It's my fault. Let's play like if it, I want to just cover, cover some of it up. If we start with the left-hand side of this, then what would be your instinct?
Change it to.
Oh, wait, let me go with that suggestion. Can we write that as natural log of secant times tangent? No. When we have secant times tangent and break it apart, it's the sum. What I'm saying.
Or I was hearing him and you together.
That's what makes me want to punch Keith every once in a while. But I don't. I never. If this was log of a product, we could take it apart as the sum of two logs, but it's the sum of two logs, not the sum of one log, or not the log of one sum. You cannot distribute natural log through anything.
Can't write it as secant times tangent.
Correct.
Okay.
And let me, I'll put this down so that
I
you
mean,
can
I
see.
said that you can't distribute the natural log. I was just asking you if you can put the natural log of it.
And that's what I'm telling you, you can't do. And I want to show you why. If I have, let me go back to where you can see, image me real fast. If that started with natural log of absolute value of secant x plus tangent x. And you know you can't distribute the natural log. But you're saying, can I change it to natural log of secant x? Are you wanting to put another natural log in there or just secant times tangent?
Secant times tangent.
Okay. So that's your question, right?
Yeah.
Okay. Instead of looking at this left-hand side, look at this right-hand side and tell me how you would rewrite that. The log of a product can be written as the sum of how many logs? Sum of two logs. So natural log of secant x plus natural log of tangent x.
Oh, and that's a thing of it as a sum. Yeah.
And that's not the same as this.
So you can't go backwards.
You absolutely can. You can put the sum of two logs back together as a log of a product. You can go this way and you can go the other way, but neither one of those equals this. This is the log of a sum.
Only one log.
That's right, that's right. It just clicked. That's one log. That's the sum of two logs.
Okay, I see now.
Okay, no, that's fine. No problem. I'm glad I could show you. All right, so we can't use our log of a product, or we can't distribute the log. The only property I see that I can use here is to put the -1 back as the exponent. Right?
Oh.
All right, that's that's in college algebra, I call that property C. It's the property that says if you have log of something to an exponent, you can bring the exponent out front. Or if you have the exponent out front, you can bring it back as the exponent of the argument of the log. So what is something to the -1? What does that mean? It's reciprocal. That means the reciprocal of secant plus tangent, 1 over secant plus tangent. And right there, you need to think the rule we learned yesterday. That denominator, secant plus tangent, if I multiply both numerator and denominator by the conjugate of the denominator would become a nice Pythagorean identity, secant squared minus tangent squared. And what is secant squared minus tangent squared? 1, so that's just natural log of secant minus tangent, which is what we needed. So that one was a little bit harder. We just had to think of, we had to start with a different property, the property log of something to a power. We can put the power out front or vice versa. So now can we do, a couple of these ourselves? Number 15 and 16, and heck, that's all. Yes.
You know what this reminds me of?
What?
A real exploding, one of those.
Uh-huh.
And then like it blows up and things go everywhere and then somehow all.
Straight down, it collapses into one beautiful little pot. I thought you were gonna say Chernobyl dogs. Madison likes information about dogs of Chernobyl. Don't you know? All right, so 15, show that natural log of absolute value of tangent x plus natural log of absolute value of cosine x equals natural log of absolute value of sine x. I'm gonna go ahead and, no, I don't have to write down 16. I've got it on my paper. All right. Any, mini, miny, mo, which side do you want to start with? I would start with the left. It looks more complicated. I would say start with the left-hand side. And then what are you thinking, Heath?
The log to sums equals a product.
Okay, the sum of two logs can be written as the log of a product. So one single log, natural log of absolute value of tangent x times cosine x. Yes, yes, please do. Absolutely. How about that? These may be the easiest ones we've done. No, you do have to know your properties of logs. But that was a 3-stepper. After we wrote down our left-hand side, it only took us 3 steps to get to the right-hand side. All right. One more, number 16. Show that natural log of absolute value of 1 plus cosine x minus 2 natural log of absolute value of sine x equals negative natural log of absolute value of 1 minus cosine x. These are the notes that you're going to look back at 10 years from now and say, I can't believe that once upon a time I knew what that meant. If you don't use it for a long time, then when you pick it up again, it just looks like Greek. Which side do you want to start with? I would. Then what?
Um,
Two things. I'm hearing two things, and actually I can do them both at once. I can put that back as a single log in just one step. As a single log, that'd be natural log of absolute value of what? 1 plus cosine x over sine squared x. Because I just put that 2 back as the exponent of the sine. And then moved it to the denominator because I was putting back together the difference of 2 logs. All right, then what?
You brought some for day.
That seems like a good thing to do because I keep glancing up here and I notice that my answer, or not answer, but my right-hand side only has cosines in it, doesn't have sines, but I know how to change sine squared into an expression with cosine. Right, it is 1 minus cosine squared. Okay, so what do you, Abigail, is that you?
Yeah.
What are you wanting to do? Factor that denominator? Okay. Then what?
Take out the.
Divide by the 1 plus cosine x in both the numerator and denominator. And I have natural log of absolute value of 1 over 1 minus cosine x. Keep looking back up at what I want to end up with.
Convert to a negative x.
Instead of that quotient, I can write the argument as 1 minus cosine x to the negative 1.
And well, a negative exponent.
Okay. And you do that one step at a time. To the negative 1. And then I can bring that negative out front. And I'll have exactly what I wanted.
Not skip the steps of
I can handle you skipping a step once in a while, like putting that back together as a single logarithm in one step. It's kind of a slippery slope, Ellie, because you go, well, if I can skip this step, why can't I just skip all of those steps if I can see from here to here in my head? Like, yeah, you can't skip all the steps. So yeah, you can, as long as I can see that, yeah, what you did, then it's okay to skip a little bit, few steps. But you got to remember you're doing a proof here. You're not trying to solve an equation and you're doing a bunch of steps in your head. You're trying to show that this equals that. And so you need to show most, if not all, of the steps of how you get from here to here. Yes. How did I get a positive 1 to be a negative 1? Where was that? This. Oh, what does the x, what's the R word that pops in your head when you see a negative exponent? Reciprocal. So this just means the reciprocal of this. The reciprocal of this is 1 over 1 minus cosine x. So I wasn't pulling that 1 out. I was saying reciprocal means the exponent negative 1. All right. No, we have never finished early. That kind of makes me nervous. So we did both of those. Could have. Or we may have gotten through more than I thought we would the previous 2 days. Love this quote from Thomas Edison. I have not failed 700 times. I've succeeded in proving that 700 ways will not work. When I've eliminated all the ways that will not work, I will find the way that will work. Y'all just aren't as susceptible as to chill bumps as I am, are you? Things impress me, I just go full body goosebump. That's a good way to think about failure. Yeah, proofs, but failure. You haven't failed, you just proved what didn't work. And you need to try something else. All right, I think that's it. I really did not anticipate finishing early. What is our next page of notes? Yeah, and that's gonna be easy, and I'm gonna give you those formulas on the test. You don't have to memorize everything that's on that page. You just have to know those formulas exist so that if you need them sometime later in your life, you can Google them. You just say, oh, I know there's an addition formula somewhere, and you look at it. There's gonna end up being more than 4 in the next. So I'm just gonna give them to you on the test. Yeah. Okay. I don't want to start that really. So what if one of 2 things, you can either get on Rome State and do that evaluation now, or you can start the homework and I'm here if you get stuck on something. Yeah, I would say if you haven't done the evaluation, now's an excellent time to do that. If you get stuck on something, wave at me. Otherwise, I'm gonna look at this homework y'all just put into. To tell you what to comment.
Why don't you comment one of the